Okay, I hope you have stuck with it so far. A bit of, some basic statistics and probability stuff. For some of you, this may be very old hat and very boring. For some of you, this may be a little challenging, but trying to make it accessible to everyone. So in this lecture and the next one, we're finally going to apply all of this stuff and set up a program for evaluating statistical hypotheses. So let's dive into it. So again, the point of the last two lectures was to just give you enough background understanding of probability and statistics that we can now start to learn how to evaluate statistical hypotheses. So that's the point of this lecture and the next. So a statistical hypothesis is a claim about a real-world population. Um, and the claim, more specifically, is that the real-world population has the same structure as a specific statistical model, right? So it's claiming a sort of fit between the world and your statistical model. So, for example, the hypothesis that most smokers in America are men, well, that's a claim about actual people in America, right, about smokers. And what is claiming, more specifically, is that the real-world population of American smokers fits a simple proportion model where the proportion of individuals exhibiting the value male, which is the value of a variable, which we call sex or gender, um, greater than 50%. And there's, well, my head's over him smoking, but James Dean smoking, not looking cool at all. Don't want anyone to think that smoking is cool. All right. So how would you examine that hypothesis, right? I mean, one way would be to look at every smoker in America and check their gender, but that's impossible practically. So this is another way that we can answer that question, right? We'll determine whether a given sample from the population, we'll just look at a subset of the population and see if in that sample we have data that provides evidence for the truth of the hypothesis. So what's the nature of this data that we're observing in the sample, right? It's going to be the observed relative frequencies of individuals exhibiting the property of interest. For example, um, say we sample 100 smokers, right, instead of however many millions there are. And we look in that sample, and it turns out that there are 55 males, so 55%, right? The question is, okay, there's some data. What we need to answer is that good evidence that more than 50% of all American smokers are male, right? Um, so we're going to talk about how we can answer that question. And in order to answer that, we're going to use the statistical theory of estimation. Okay, a little bit of gets a little mathy for a second here, but stick with me. I'll try to take it slow. So for any property, or we could also say value of a random variable, call that variable A. There's going to be some probability of A in the population. So we'll call that PA, or probability of A, right? So in the United States, there's some proportion of smokers that are male, right? We don't know what it is, but whatever that is, that'll be the probability of, say, M or whatever, right? For being male. Um, okay, so that's what PA is, right? It's about the real world, the actual probability of that value occurring in the population. Now, a random sample from the population, right, will exhibit a relative frequency of A. So we'll call that little f A, right? Same thing, right? It's just from our sample, we notice 55% of the smokers are male, right? Um, Typically, we don't know PA, that's what we'd like to know, but we can know FA, right? We can know the relative frequency in our sample. So estimation is a statistical technique for using that thing we do know, right? The frequency, the relative frequency in the population, right? And using that as evidence for some claim about, right, the probability in the actual population. So let's go back to the marbles, right? Keeping it simple. Hopefully you should be familiar with our jar of marbles by now. Um, we've got two variables, color and size, and then each of those variables has two possible values. So a marble can be either red or non-red, and it can be either large or small. Um, let's say half the marbles in the jar are red, right? As we just said, typically we don't know PR in the population. Let's talk about a population where we do know, right? So that we can sort of establish the relationships that would hold between between a sample and a population, and then we can apply it to situations where we don't know proportions of the probability of the population, right? So let's say that we know half the marbles in the jar are red, so PR equals 0.5. We then determine sampling probabilities for various values of FR and samples of different sizes, right? So we've already done that in the last lectures. So we know that, for example, when the sample size is 100, when n equals 100, the probability that from a sample of 100, exactly 50 would be red is 8%. And that feels like kind of a low probability, being that that is the actual, right, probability in the population. Um, like the relationship between our sample and the population is sort of not super helpful if that's the case, right? Well, there's a way to get around this, right? We need to answer sort of two questions. So 8% feels low, but maybe we should answer the question, so how high of a probability would we want, right? What do we need in order to have good evidence for a claim? And then what sort of claim about the relative frequency in R could we make that gave us such a suitably high probability, right? So the answer to the second question will depend on the answer to the first question. So let's look at these in order. The answer to the first question is 95% probability. This is just sort of the standard that's been accepted by the scientific community. We want a 95% probability, right, that the probability in the actual population sort of matches our relative frequency. Now, the answer to the second question, right, what sort of claim could we make about the relative frequency that would give us that level of confidence? That will be that will involve the notion that we talked about before, standard deviation, right? If you remember the notion of standard deviation, you might recall that the probability that relative frequency of the sample will be within two standard deviations of right the probability or the in the population or the mean, right, is 95%, right? That's convenient. 95% is our goal. Well, there's a 95% probability that our relative frequency is going to be within standard deviations, right? Now, that's the case for any sample size, right? Standard deviation is independent of sample size, but with a larger sample, you're going to have more of the values within two standard deviations, right? So for a sample size of 100, two standard deviations includes all values of the relative frequency of R from 0.4 to 0.6, right? So we can say that there is good evidence. Now remember, here we know the actual proportion in the population. We're not working backwards. So given that we know that there's good evidence that a random selection of 100 marbles, right, from a population with a probability of R of 0.5, that we're going to get somewhere between 40 and 60 marbles that are red in that sample with 95% probability. Certainly, it's always possible, right, that our sample could be all non-red. There are 100 non-red marbles in that jar, but the probability of that happening is incredibly low, right? So you can have outcomes in that extra 5% that's outside our range, but you can never really have, you're never guaranteed, right, a certain proportion, but you can have very good confidence, 95% confidence that it'll fall within a certain range. So that's the sort of claim that we can make about the relative frequency from a sample that will give us the sort of right confidence that we want. Okay, so that was useful, right, to explain, um, given that we know the probability, right? But now in the cases that we're going to be examining, right, where you're trying to come to some conclusion about the population and right, answer a question you don't know about the population based on the sample, now we need to see how to make that inference right backwards. So we can do this by sort of simply adding 2 standard deviation to whatever relative frequency we find in the sample, right? So, for example, when n is 100, so a sample of 100, 2 standard deviation is going to be about 0.10, right? As you recall, the probability in the uh, in the population was 0.5, right? So we were going to sample 100 marbles from the jar, and let's say we happen to find 50 red, right? We just happen to find the exact actual proportion that there is. We don't know that. We don't know what the actual proportion is in the population, let's say. Um, what we do know is that 2 standard deviations, right, from 0.5 is 0.10 in either direction, right? So we do know that if the relative frequency is 0.5, that with 95% certainty, we can say that the proportion, the probability of red in the population is 0.5 plus or minus 0.1, right? That it's that same range from 0.4 to 0.6 that we discussed in the last slide, right? Just sort of working backwards to it. Now again, just because we find that in the sample, it's not a guarantee that the actual probability of red in the actual population is 0.5, but it will be 95% of the time, right? If you sampled 100 times, um, the vast majority of the time, it's going to fall in that interval, right? So again, we call this the 95% confidence interval. So when we're talking about estimation, um, this sort of 2 standard deviation value we call the margin of error, right? So we might say that the probability of R in the actual population is equal to the relative frequency of R in our sample plus or minus the margin of error. Now in this case, we're supposing that we found a relative frequency of 0.5, right? 50 of the 100 marbles we sampled were red. And then we can say that plus or minus 0.1, right? The probability in the population will be 0.5 plus or minus 0.1, or in other words, between 0.4 and 0.6. And we can be 95% confident. So the big takeaway here, right, is that when we're talking about estimation, right, when we're taking a sample and then trying to work backwards to some probability in the population, we're going to be dealing with intervals, right, a range of values. So you certainly cannot simply equate the relative frequency you find in your sample with the probability in the population. You're going to be wrong the vast majority of the time, right? Because recall, um, the probability of getting exactly 50 out of your 100 red is only 8%, right? Um, so that's why we're going to be talking about intervals, about ranges of possible values. So the specific values that are going to lie within that margin of error will depend on the sample size. So larger sample size, you're going to have more values within that, or sorry, fewer values within that margin of error. Um, so we have this was sort of, right, the point of those figures. I don't know if you recall, we took larger and larger samples and you saw sort of the probability of getting sort of the mean came down, right? But they were all sort of starting to group together. Um, so we can see here on this chart, right? So we sort of stopped at about, I think, 4 and 5, right? Samples of 4 and 5, and then we just showed you the distributions you'd get for up to 500. So this table goes up to 10,000, and you can see here, supposing that we're talking about a sample frequency of 0.5, right? Which is obviously the sample frequency you actually get in any given sample could vary widely, right? We're just using 0.5 as an example, right? Um, but if it were, and your sample size were 10, right? Well, to have 95% confidence, we'd have to say that the actual probability in the population ranges from 0.18 to 0.82, so a very wide margin of error, right? A 0.32 or 32% margin. And remember, that's on either side, right? So you got a range of 4%, right? And then if you look down at 10,000, sample of 10,000, right? Um, here, if you found a relative frequency of 0.5, so 5,000, right, of the 10,000 marbles you sampled were red, you can be confident that with 95% certainty that the probability in the actual population is between 0.49 and 0.51, right? So a margin error of, I believe it'd be 0.01, right? My head's over, but on either side. And so on that same page or the next page, they give you a sort of rule of thumb, a little sort of like um, handier version of 6.1 that sort of rounds things off. It makes it maybe something you could even potentially memorize or at least consult very quickly and easily to get a sense of like, okay, if I'm dealing with a sample size of 25, I've got a margin of error, right, of like 25% on either side, and so on, right? If I'm dealing with 500, 0.05, and you might find that handy. And then if the sample size is somewhere in between, right, you can kind of guesstimate a little bit, and you say, okay, if its sample size is 250, it'd probably be halfway, more or less, between 100 and 500, so something like 0.07, right? 0.075, I guess. So that's the idea. So if you get a sample size of 25, right, for example, and you find a sample frequency of, say, 55% of males among the smokers you sample, um, well, the margin error is plus or minus 25%. So if you want 95% accuracy, what you're saying is the proportion of males in the population of smokers is somewhere between 30% and 80%, right? A very wide margin. Um, Sample size of 500, we've got a much smaller margin of error, only 5%. So again, if you found 55% males in your sample, well, the probability in the actual population would be somewhere between 50% and 60%, right? A much smaller range. So bigger sample size, smaller margin of error, right? And so you can be more at 95% confidence, you've got a tighter range. Here's just sort of a diagram of how we work backwards, right? So we've got our sample, the size of the sample is n, we find some relative frequency, and then we estimate backwards, right, to the population. We say, well, given this relative frequency, we think that the probability of A in the population is the relative frequency we found in our sample plus or minus the margin of error. So we've adopted, again, a 95% confidence level as our sort of like standard. Um, so that means that the probability of the interval relative frequency plus or minus margin of error, including the true value of the probability in the population, is 95%. Um, now you could decide on a different standard, right? Maybe you want a confidence level of 99%. And if you don't change your sample size, that just means that your margin of error is going to get bigger. right? So in our original sample of 100 marbles, 95% confidence gave us a range of values from 0.4 to 0.6. If again, if our relative frequency we found in our sample was 0.5, right? We can say, okay, with 95% confidence, we know that the probability in the actual population is between 0.4 and 0.6. Now, if you want to broaden that out a little bit and include a whole range from 0.38 to 0.62, you can say with 99% confidence that the probability of A in the actual population lies between 0.38 and 0.62. So you kind of hopefully are seeing how these relate, right? If you're holding your sample size constant, there's a trade-off between confidence level and margin of error. I can be more confident in a wider range of values, right? Or if I want to narrow my range of values, I'm going to be less confident that the actual proportion falls. Now, part of the reason we've been sticking with a sample frequency of 0.5 is because it gives us a nice symmetrical margin of error. It's not always the case that the margin of error is symmetrical in that way. As the relative frequency sort of moves closer to 0 or 1, right? If you're finding like 100% smokers or 100% males in your sample of smokers, or if you're finding no males in your sample of smokers, um, you're going to get a less symmetrical margin of error. It's kind of getting squished up towards the edge that it's moving toward, right? Um, but we can pretty much ignore this, right? If the relative frequency you find is anywhere between 0.1 and 0.9, the distortions that are introduced are small enough that you can largely ignore them. Just keep that in mind, right? If you're beyond those bounds of 0.1 and 0.9, our rules of thumb are going to become less accurate. But for the purposes of this course, you won't need to worry about it as far as like exercises and stuff. Okay, so now we can apply what we've learned talking about evaluating distributions. So here's figure 6.2, right? It shows how this works when there's more than one variable, right? So when we're dealing not just with a proportion of the population, but a distribution, right? Where you've got more than one value, more than two values of a variable. So we're no longer just red and non-red. So what if we are talking about, right, a jar of marbles and we're interested in more colors? We're interested in whether it's blue or green or red, right? So how does estimation work in that situation? Okay, well, let's take a random sample of 250 marbles from our jar, right? And let's suppose that gives us a frequency of red of 56%, right? So 140 red marbles out of our 250. The relative frequency of greens, 0.24. The relative frequency of blue is 0.20, right? And you can see over on the right that equates to finding 50 blues that are a sample of 250 and 60 greens that are a sample of 250. So consulting our table, right, our rules of thumb, the margin of error for a sample of 250 is plus or minus 0.06 or 6%, right? So we can see then on the top there, estimating backwards, right, our estimates for the probability of red in the population of in the jar of marbles is going to be 56% plus or minus 6%, right? For green, it's going to be 24 plus or minus 6%, and for blue, it's going to be 20 plus or minus 6%. Okay, so we have estimated, right, proportions. We've estimated distributions. So now we want to use samples to evaluate correlations in a So an evaluation of a correlation can come to one of two conclusions. Either the sample frequency does provide evidence for the existence of a correlation, or the sample frequencies, right? There might be more than one sample frequencies if you're dealing with more than one variable. They might fail to provide evidence for the existence of a correlation. I guess you will always have more than one, right? If you're talking about a correlation, right? So the sample frequencies never provide evidence that there is no correlation, right? And this is because there's always a margin of error, right? Recall that no correlation means that, right, the proportions of the two variables in the population are exactly the same, right? And with a margin of error, you can never know that. You can never know that they're exactly the same. There's always the possibility that they're different. Okay, back to our jar of marbles that only has two variables, right? Color and size, and only two values for each. We got red, non-reds, larges, and smalls, right? And now this time, let's say we don't know the proportions in the actual population. So we take a random sample, this time 600 marbles, right, from our jar. It's going to be a big jar, right? Um, so in that sample, 500 turn out to be red, 100 turn out to be non-red, and then among the reds in the sample, 325 out of 500 are large. Right? So using the notation for conditional probabilities and adapting it to sample frequencies, right, we've got the frequency of large, right, conditional on being red is 65%. And then the frequency of being large, conditional on being non-red, will be 35%. So in the sample, we definitely see a difference, right? And, again, the frequency of large conditional on red and the frequency of large conditional on non-red. The question is this good evidence of a correlation in the population? Well, this is sort of important to keep in mind because this will matter when you eventually have to calculate these things. So pay attention right here. To estimate the proportion, the probability, right, of large conditional on red in the population, you don't want to use the whole sample size of 600, right? You're only using the ones that turned out to be red. So there were 500 reds, right? So that means that when we're figuring out our margin of error, you want to find the margin of error for 500, not for 600, right? You go to our chart, the margin of error for a sample size of 500, 0.05, plus or minus 0.05. So given the sample frequency, right, that we found, the probability of large, right, a marble being large, conditional on its being red, is equal to the sample frequency of large conditional on red plus or minus the margin of error, which is equal to 65 plus or minus 5%, right? So we got, you can see up in the chart on the top, right? On the red side, our estimate is between 60 and 70%, right? We have 65 plus or minus 5 on either side. Okay. Now the non-red marbles, there were only 100 of those, right? So now when we're calculating the margin of error for that probability in the population, we want the margin of error for 100, right? The margin of error there is 0.1, right, or 10%. The probability of large conditional on non-red in the population will be equal to the sample frequency for large conditional on non-red plus or minus the margin of error, which is equal to 35 plus or minus 10%. And you'll see that illustrated on the top on the right there, right? So 35 plus 10% is 45, 35 minus 10% is 25. So our interval there is between 25 to 45 on the non-red side. Okay, so notice the two interval estimates do not overlap. Right? We got 60 to 70 on the left. We got 25 to 45 on the right. Right? There's a nice gap, about 15% in between 45 and 60. So that is good evidence for concluding that the probability of large conditional on red really is larger than the probability of large conditional on non-red, which is just to say that color and size are correlated in the population. Being large is positively correlated with being red. So if anything I said you didn't follow, I think this is an important slide to pause and convince yourself that everything that I've written there is true and illustrated in that graph. Okay, now let's change the case slightly and show an example of lack of evidence for correlation. So suppose that instead, the sample frequencies that we observed of large marbles among the red and non-red were 325 out of 500 reds, right, were large, 65%. And let's say that 55 out of 100, or 55% of the non-reds were large. Okay, so the samples are the same, right, 500 and 100. So the margins of error are the same as before, right? For the reds, the margin of error is 5%. For the non-reds, the margin of error is 10%. But the sample frequencies are different now, so we got to run the math again. So this time, right, the probability of large conditional on red in the population is equal to the sample frequency of large conditional on red plus or minus the margin of error, and that will be 65 plus or minus 5%, right? So look in the left top, and you've got between 60 and 70% once again, right? But that's the same as before, right? But this time, the probability in the population of large conditional on being non-red will be equal to the sample frequency, right, of large conditional on non-red plus or minus the margin of error, which is 10% again. But this time the number is 55 plus or minus 10%. So our interval on the top right there will run between 45 and 65. So now we got an overlap, right? The lowest value for red is 60 and the highest value for non-red is 65. What does that mean? That the interval estimates overlap, right? That means that for all we know, the proportion of large marbles in the population might be 62%, say, for both red and non-red marbles. That would mean there's no correlation at all between size and color, right? They could, for all we know, have the exact same proportion. But as we've said, just because that's possible doesn't mean we have good evidence that there's, right, no correlation, right? For all we know, it could be 70% and 45%, right? So the appropriate conclusion to draw when we have an overlap like this is that there's no good evidence for a correlation between the variables in question. We don't conclude that there's evidence for no correlation. Convince yourself that those are two different claims, right? Okay, so now, how do we estimate the strength of a correlation? So you might recall, right, that the first time we encountered strengths of correlation, we had a sort of a quick and dirty way of calculating the strength, which is taking the difference between the two proportions in the population, right? So, for example, again, right, we way back, whatever, 2 lectures ago, when we saw that 75% of the red marbles were large and 25% of the green marbles were large, we could say the strength of the correlation between being red and large was 0.5, right? 75 minus 25. But in the current case, we don't know the proportions, right? That's the whole question we're trying to answer. We only have these interval estimates. But we can still do a similar thing. We can take the differences between the highest and lowest values in the range. So in figure 6.3, right, this is the one, again, where there was a correlation, right? The maximum possible difference that there might be in the proportions would be 70% minus 25%, right? And then the smallest possible difference that there might be is 60% and 45%. So we'll take 0.7 minus 0.25, so that's again the widest range, right? 0.45, and then we'll take 0.6 minus 0.45, so 0.15 is the sort of the smallest range. So then we can say the estimated strength of the correlation is the interval 0.45 comma 0.15. So the strength of the correlation is somewhere in there between those two values. Now let's compare that to our example where we had no evidence of a correlation because we had overlap. And there, the biggest possible difference, right, between the reds and the non-reds is 70% minus 45%, 0.25. The smallest is 60 minus 0.65, which is actually a negative number, negative 0.05. You can have negatives here. So the estimated strength of the correlation here is the interval between 0.25 and negative 0.05. So this will happen when intervals overlap, right? The minimum strength will be a negative number, right? We've also got 0 in that interval, right? So this interval for the strength of the correlation is consistent with a positive correlation, no correlation at all, or even a negative correlation. Okay, so those last few slides was a lot coming at you fast, and these are all important things you'll need to be able to do and calculate, and you'll practice these right in the homework, but go look at those again, right, and make sure that you can sort of do all that stuff that we run all those calculations. And right, the math is not so hard. It's just sort of keeping it all straight in your head, and the way to do that is practice. Do the exercises I've assigned, and if you're still not feeling confident, do more exercises, right? You can do more, and then take them to discussion section or take them to my office hours and ask, did I do this right? Um, okay. Uh, Confidence levels for correlation. So the method we've used is assuming that the margins of error for the differences between the proportions are sort of the same as the margins of error for individual proportions. And what we just did is, strictly speaking, a little wonky, right? If you were a statistics sort of guru, you would have said, "Hey, what's going on here?" Right? The reasons are really not super important, right? But broadly, conceptually, right, you can see that like um, when we're taking differences, right, a difference is going to be sort of consistent with a number of different sample frequencies. So the difference between 0.3 and 0.2 is going to be the same as the difference between 0.5 and 0.4, right? And so that's going to mess with the standard deviation for differences, right? It's going to be different than the sample frequencies. But the upshot of all that is actually that we end up, by using sort of the simpler method for evaluating strength of correlations, being actually a little stricter than we would if we had done the more complicated version. So essentially, we're calculating for 99% confidence when we evaluate the strength of these correlations. So we're actually being a bit conservative, but I mean, there's no real harm, right? If you have to err on being sort of more conservative and more confident, right? Again, these, every once in a while there'll be a slide where I'm saying, okay, what we taught you is strictly speaking not like technically right. It's kind of a rule of thumb or a quick thing. That's just if anybody cared or noticed, right? It was like just letting you know that we know, right? But it's not something you need to know for exams. Okay, statistical significance. So the notion of statistical significance um, is going to apply for our purposes primarily to differences between sample frequencies, right? So there's going to be two factors that contribute to differences that you will find in sample frequencies. So one will be the actual difference. There might be a real difference in the proportions in the population, right? If there is, you are likely to find a difference in sample frequencies, right, between two variables. Um, but there's also a possibility that there's just random variation introduced by the sampling process, right? Again, you're not guaranteed that the sample frequency of your sample is going to be exactly the same as the proportion in the population. In fact, there's a relatively low probability that will happen. So there's always going to be differences, right, between your sample and your population. Um, so statistically significant differences, right, are differences that are unlikely to have been produced just by random variation in the sampling process, right? So if I'm saying, oh, I noticed a difference in the sample frequencies here, right, between say right, being red and large and being red and and being non-red and large. Um, to say that that difference is statistically significant is to say, I think this is because there's a difference in the population, and it's not because of just the random variation you get from the sampling. For us, we've already figured out how to tell if something's statistically significant. It's if the interval estimates don't overlap, right? We've already seen that. Um, and if they do overlap, then the differences in the sample frequencies are not statistically significant. And that's basically all there is to it, right? You already know how to do it, right? So, and you might sometimes hear things about results being statistically significant at the 0.05 level. And essentially, this just means that the results are statistically significant using 95% confidence interval, which is what we've been doing. So you already know how to calculate. So what does that mean? Sometimes you will read um, scientific articles, right? And all they tell you is that there is a statistically significant difference, right? They may not give you the actual sample frequencies, and that is definitely less informative, right? You'd much rather have this actual sample frequencies, um, but it's not nothing. It does tell us something, right? So suppose you read a report about a jar of marbles, right? Somebody published a scientific article about a particular jar of marbles with right some red, some non-red, some large, some small. And say the report says that the difference between the sampling frequencies of large marbles among the red and among the non-red is statistically significant, with a greater percentage of large among the red. That's exactly just what we did a little while ago, right? Um, okay, if that's all they tell you. What could you say about the strength of the correlation, right? You don't have the sample frequencies, so you can't take the difference. Um, we know that there's a positive correlation between large and red population. That's was implied by them saying it was statistically significant. Um, we know the strength of the correlation is greater than zero, right? Um, but that's it. That's all we know if we don't have the sample frequency. Um, now, if the report claimed no statistically significant difference, but again, didn't tell us the sample frequencies, what could we infer from that? Well, in that case, it's going to matter quite a bit what the sample size is, right? So if you have a small sample size, you know the intervals overlap, but you also know that the margin of error is going to be really large, right? So they're going to be very large intervals that are overlapping. So there might be no difference at all, or there might be quite a large difference in the sample frequencies, right? Because these margins of errors are so large. So a report of no statistical significance with a small sample size is a pretty uninformative result, right? But a report of no statistically significant difference with a large sample size is fairly informative, right? Um, Margins of error are going to be very narrow, right? And so if they don't, right, and if they overlap, right, it's possible there's a correlation there, but if there is, it's going to be a very weak one, right? So that can be helpful. Right? That can tell you something. And we have a little table 6.3 that sort of summarizes these relationships. If you just get a report of a statistically significant, right, or not statistically significant um, difference, but they don't give you the sample frequencies. This is what you can know from them, and it's honestly not a lot, right? Okay, so evaluating correlations, a quick and dirty method, right? So here's another thing you could do. You could take the sample sizes of the two relevant partial samples. So recall, right? We had a sample of 600, but then when we're calculating margins of error and trying to evaluate a correlation, for the 500 red, we used 500 as to look up on our table for a margin of error, and then the 100 non-reds, we used 100 to look that up on our table, right? And then you use those rules of thumb, add the margins of error together, and then see if the observed difference in sample frequencies is greater or less than that sum of the margins of error. If the difference is greater, it's statistically significant and you have evidence of a correlation in the population. If the difference is smaller, then you don't have evidence of a correlation in the population. And finally, if the difference in sampling frequencies is statistically significant, the sum of the margins of error from the difference in the sample frequencies would give an estimate of the minimum strength of the correlation. So this is just doing what you did before with the chart, right? So I would say only do this when you first start calculating these. Go up, draw your chart, find overlap, right? Now here's a quick way to do some math that's equivalent to that. If you're really confident um, in the charts, then you can just use this method and it'll give you the same result without having to sort of draw. So again, here's our quick and dirty method. So two partial sample sizes, 500 and 100. The margins of error would be 0.05 and 0.1, so the sum is 0.15, right? Again, we looked those up in the tables to find them. Well, the difference in the observed frequencies is 0.65 minus 0.35, which is 0.3. So 0.3 is greater than 0.15, so statistically significant, and we have evidence of a correlation. And then the minimum estimated strength of that correlation will be 0.3 minus 0.15, which will be 0.15. So again, only start using this quick and dirty method if you feel you've mastered the slower drawing out the chart method. And then if you really feel like you got it nailed, then it'll be fairly obvious why this is right, basically equivalent to doing that. Okay, so that's that. Again, there's a lot, right? I know that these 2 weeks, quite a bit of like some mathy stuff. It's just this is science, a lot of important stuff for your life. So this is how you can evaluate it, and I think this text does about as good a job as you can do keeping the math as really, really simple, right? Trying to you really I don't think you're gonna make a lot of mistakes with the math. You need to keep track of the concepts, right? And if you've got the big picture of the concepts, it'll keep you on the right track. So again, do try the exercises. If you feel you're not getting them, go to discussion, go to extra discussions, ask questions, come to my office hours, send me emails. I want you to get this stuff. All right, thanks.